earlier this week, we proved that the fundamental group is a topological invariant. So if you have two spaces that are topologically equivalent, then they have the same fundamental group. And today we're going to discuss this in a little bit more general context. So the main definition, well, there's two definitions. So first we say maps F0 and F1 between two spaces, X and Y, are homotopic, which we write as in this way. If there exists a map F, let me call it H, from X times the interval into Y, so that H restricted to X times I is Fi for I is 0 and 1. Okay, so I guess the picture of a homotopy is here's X times the interval. Nope, the other way around. This is X and here's the interval direction. And at time 0, we do F0, and at time 1, we do F1, and in between we interpolate. And these are maps into some other space Y. So this generalizes our notion of homotopy between of loops. And yeah, okay, fine. And we say X and Y are homotopy equivalent if there exists maps between them, let's say F and G, so that G compose F is homotopic to the identity on X, and F compose G is homotopic to the identity on Y. Okay, so this, well, okay, so let's see some examples. So first of all, the first example is if X is homeomorphic or topologically equivalent to Y, then this implies X is homotopy equivalent to Y. Right, so here we write this as X homotopy equivalent to Y. So one fewer line than topologically equivalent. And this is because, well, if there's a homeomorphism, then these maps F and G are, the compositions are equal to the identity, okay? And that's stronger than being homotopic to the identity. Right, so okay, so that's the first example. A non-trivial example is that the circle is homotopy equivalent to R2 minus the origin. So let's see why this is true. Yeah, okay, so we need maps between them, say F and G. So there's an obvious map for F, since, well, if we think about the circle as embedded in R2, then we can just take F of X to be X. And for G, we can define, let me say G of Y is Y over the norm of Y. So this will be a point of norm 1, so we get a point on the circle. So now let's look at the compositions. So if we do F then G, so this is G of X, which is X over norm of X, but X is on the circle, so the norm of X is 1, so this is just X. So from this computation, we see G compose F is the identity on the circle. But the other composition is not the identity. If we do F and then G, then, well, so this is F. So G of Y is Y over norm Y, and F is just the inclusion, so this is Y over norm Y. So G composed with F it's not the identity map. It sends Y to Y over norm Y. But we only need for this to be homotopic to the identity. So F compose G is homotopic to the identity on R2 minus 0 via the straight line homotopy. So, okay, I guess we could write a formula. So I guess H of YT is 1 minus T times Y plus T Y over norm Y. So an important point is that this homotopy, well, okay, so let me draw a picture, because this might seem trivial, but there's actually, I mean, there is one thing to say. So given some point Y, the projection, so G of Y is this point here. So Y over norm Y. And the straight line path between Y and G of Y, so this is G of Y, this is what the straight line homotopy does. It interpolates between the point Y and the point on the circle along the straight line between them. That's this formula. But it's important that this line doesn't go through the origin. So for any point that we pick, this path from Y to G of Y, it doesn't go through the origin. So this is a homotopy of maps of the plane minus the origin. Okay, so that's all right. So we see here that so that this proves that these two spaces are homotopy equivalent, despite the fact that they're not topologically equivalent. I guess we haven't proved they're not topologically equivalent, but well, it is true. Okay. Well, let me give you one more example. So the torus minus a point is homotopy equivalent to a wedge of circles. So let me explain this. So, okay, here's the torus. I want to think about it as quotient of the unit square. And removing a point, let's just remove this point in the center. And the wedge of circles, it's actually a subspace here. So we have this boundary subspace is topologically equivalent to a wedge of circles. I mean, it's, so we have, because all these points are the same point. So if you just think about what space that is this wedge. And right, so there's a map. Well, okay, so again, we have a inclusion. So we have like the wedge going to the torus minus a point. You can use the inclusion. And for the map in the other direction, let me say like project radially. So let me draw, so given any point, we just draw sort of a straight line from the point we're removing to through that point. So that would, well, okay, like if I can draw a straight line, and then that will hit the boundary at some point. So here we have like X and then R of X. And we just do this, we just project radially from this center point. And well, I mean, this picture actually also shows you, so again, what we'll see is that if we include and then project, we just have the identity. But if we project and then include, that's not the identity map, but it is homotopic to the identity map. And the homotopy is kind of indicated in this picture. So here, these lines are indicating a path, indicate a path from any point to point X to R of X. And if you just interpolate along that path, you get a homotopy from the identity map to the map R. Okay. All right. Right, so the main thing I want to mention about homotopy equivalent spaces is that they have the same fundamental group. So this is a strengthening of the result that we saw before, that if you're topologically equivalent, then you have the same fundamental group. So here we say that the fundamental group is a homotopy invariant. And let me just remark, so I don't want to prove this now, I think for the sake of time. I believe you can read it in Armstrong. It requires a little bit more than I want to do right now. And yeah, I want to move on to a little bit more interesting things. But let me just remark that this is reasonable since pi1, I mean, it's defined in terms of homotopy. Pi1 is homotopy classes of maps. So, I mean, right. Maybe saying this is not super convincing, but we've defined the fundamental group as we're looking at paths or loops in our space, homotopy classes, I should say loops. We're looking at loops in our space up to this equivalence given by homotopy, which is like you can deform things and deform loops. And I don't think it's too much of a stretch that, well, so the theorem is saying that if you deform your space a little bit, which is what homotopy is capturing, then you're not going to change the fundamental group, since the fundamental group is defined in terms of homotopies. And if you deform the space, then you're just like deforming the loops. That's kind of a hand-wavy intuition, but okay. If you want more details, I would encourage you to read the book. All right, so an example, illustration of this theorem. So here's some spaces that all have the same fundamental group. So we have the circle, the annulus, the Mobius band, and, well, okay, I mean, there's lots of spaces I could put here. Let me, R2 minus the origin. Let me give you one more actually. And let's say C was the space that was on the midterm. So this is like the circle, wedge, and interval. So, okay, on the midterm, for example, you show that these spaces C and the circle are not topologically equivalent, but in fact, they are homotopy equivalent. So these spaces are all homotopy equivalent. And hence have the same fundamental group, which is the fundamental group of the circle, which is C. Okay, so this is quite a useful, this theorem is quite useful because homotopy equivalence is much weaker than topological equivalence. So if you know that two spaces are homotopy equivalent, then you know they have the same fundamental group. So even though we don't know, even though not all of these spaces are topologically equivalent, we can compute all their homotopy or their fundamental groups. We know all their fundamental groups are the same. Okay. And some of the, yeah, so some of this will be on homework 7. Well, I guess we proved one of this. Yeah, so some of this will be on homework 7. Okay. So now I wanted to give you one more application for now of this computation of the fundamental group of the circle. So this is an application to the fundamental theorem of algebra. Okay, so this is an illustration of the power of topology to prove things outside of topology. So here's what the theorem says. So let me remind you, or maybe tell you for the first time. So let's fix some n at least 1. So the theorem says a complex polynomial, I guess, let me just say a polynomial. So this is like P is, let's say x to the n plus a1 x to the n minus 1 plus up to an with ai complex numbers. So it's a polynomial with complex coefficients, has a root in C, which is to say there exists some complex number beta so that P of beta is 0. So if I plug in beta for x, then I get 0. Okay, so this is what the theorem says. And so let me just point out that here, so n is at least 1, which means the polynomial has degree at least 1. It can't be a constant polynomial, otherwise it wouldn't be true. But okay, so every polynomial of degree at least 1 has at least 1 root. All right, and maybe I won't try to convince you this is an important theorem. Well, okay, look, it's the fundamental theorem of algebra. So here's the topology proof. And I'm just going to sketch it, although it's not hard at all to make this rigorous. So we'll prove this by contradiction. All right, so to start, for r greater than 0, let's let CR be the loop in the complex plane given by CR of t is r e to the 2 pi I t. So this is a loop that traverses the circle of radius r. So it starts it's based at the point r. So here, yeah, r is just some real number. Right. So now, if P, so okay, by contradiction, we suppose P is a polynomial with no root. So if P has no root, then we can just look at P compose C of R. This is a loop also in C without the origin. I mean, in general, it might be the case that, well, the image under P maps through the origin. If there's some root, then that's going to be the case. But if there's no root, then the image of C sub R, this is also some loop that misses the origin. So P compose C of R defines an element of pi1 of the complex numbers minus 0, which this is isomorphic to Z. I think we saw last time the fundamental group of R squared minus the origin Z, and that's topologically equivalent to C minus 0. Right, so we get an element for each R. So technically that element isn't exactly this loop because, well, okay, there's a little base point issue, but this isn't so important. I'm going to ignore that. So now what we're going to do is to think about what element this is. Oh, right, and let me also point out that CR and CR prime are homotopic. So for every R, we get the same element of the fundamental group. Okay, so this is going to be crucial. Okay, so now let's just think about what that element is. So, so claim 1 is for R small, CR is homotopic to a constant. And this is just by continuity. So, well, we know that. So here, what I'm saying is, so okay, so we have R is supposed to be small. So we're looking at CR, really small. It's very close to the origin. Yeah, and then we look at its image under P. And by assumption, P of 0 is some non-zero complex number. So we have P of 0. It's some definite distance away from 0. Otherwise, if P of 0 was 0, 0 would be a root, and there's no roots. And so C of R, whatever it is, by continuity, it has to be close to here. So P of C of R. So by continuity, P compose C of R is near, well, yeah, it is contained in a ball of some radius around P of 0. And so we can homotope C of R to a constant in this ball. I mean, this ball, you choose epsilon so that this ball is contained in, it doesn't intersect 0. So, okay, so you just pick the ball small enough, and then that tells you how small R has to be, and then, okay, so here's the ball. Okay, so well, we figured out what loops this C of R is. It's the trivial loop in the fundamental group. Okay, so on the other hand, so claim 2 is that for R really large, P composed C of R is homotopic to, say homotopic to the map F, which sends T to R e to the 2 pi I T to the N. And well, you can show this using a straight line homotopy. So I'll leave this to you as an exercise. But in order to do the straight line homotopy, you have to be sure that, so this is a homotopy of maps. So let me just say, this is a homotopy of maps in C minus the origin. So it's crucial throughout all of this that you miss the origin. So if we're just talking about loops in C, they're all homotopy equivalent. Right, but in C, if we puncture the complex plane, then there are loops that are not homotopic. And so, okay, so if we really want to say this homotopy is through loops that miss the origin, and so that's sort of why there's some work to do here. Okay, but now, we're done. So here F, what does F do? I mean, F is, well, F is homotopic to e to the 2 pi I T times N, which goes around the circle N times. And we saw from our computation of the fundamental group of the circle that this element, I guess, I mean, it has to miss the origin. So, okay, so you do this N times. This element is non-trivial in the fundamental group of the circle and also in the punctured complex plane. So from this, we combining, so claim 1 plus 2 imply that the loop T goes to e to the 2 pi I nt is homotopic to a constant. Which contradicts our computation for the fundamental group of a circle. So here we're using a few things. So first of all, n is at least 1. So this is a non-trivial loop. So the assumption of the theorem, remember, is n is at least 1. And right, so claim 2 is saying that P composed CR is homotopic to this map that I've written here. But on the other hand, P composed CR for R small, so that was for R big, and for R small, we get something homotopic to a constant. But all of these P composed CR, I guess I maybe should say P, this should have been P here, are homotopic. So adding all of that up, this map is homotopic to a constant, which is the contradiction. And that's the proof of the fundamental theorem of algebra. Okay, so I wanted to give you a little demo of illustrating this argument. And okay, so here we're in Mathematica, and what I'm the first few lines of this code just produces a random polynomial. So this is, the coefficients are going to be these random integers between minus 100 and 100. So you can just, so it spits out these 5 numbers, and then we define the polynomial, and then here's an image of it. And you can produce, you could just kind of do this and see, you get, right. And what I've drawn here is the image of the unit circle under this map. So this is a parametric plot here. We're doing the polynomial evaluated on the real, wait, what am I doing? Yeah, right. We're just evaluating on each of the 2 pi it. So that's the unit circle. And we're doing it from t from 0 to 2 pi. So these pictures are kind of pretty, and it's kind of fun to just let Mathematica just give you random polynomials, and you get to see what the image of the unit circle looks like. And you get these pretty patterns. Let me, I could kind of do this all day. Oops. Let me get a nice one. I mean, this one's nice. Ooh, that one's also kind of nice. Okay, one more, sorry. All right, yeah, let's work with this one. Okay, so, oh no, sorry. I'm sorry, I want to pick a different one. Ooh, pretty, that one, that's a winner. Okay, so now this next plot, for any, right, so remember in this proof, what we're doing is we're looking at the image of a circle centered at the origin, and we want to know what element in the fundamental group of the complex plane minus the origin we get. And we know from our computation of the fundamental group of the circle that the fundamental, what loop we get in the fundamental group is determined by basically how many times you wind around the origin. So this loop, we can just sort of, so okay, I'm just letting a dot traverse around this loop. And as it goes around, you just see, you'll just look how many times it winds around the circle. So it does quite a bit of winding, but most of that winding is not around the circle. So right now, or it's not around the origin. So, okay, here it winds. Well, yeah, right. So you're supposed to kind of imagine you can just kind of project this, radially project from the origin onto the circle, and you get a loop on the circle, and you can see how many times it winds around. And it, I guess, yeah, one way to measure that is if you draw, well, okay, so this one winds around twice. So all of this extra stuff, it doesn't actually contribute to winding around the origin. Okay, so that's what that is. And then I have one more animation. Oh, great. So let's see. So this animation, it's here, I'm varying R. So I'm looking at the image of the circle of radius R now. And R is going from very small to very large. So from 0.1, very close to the origin, a very small circle around the origin, to a very large one. And what we want to compare is the winding number as we go along. So so let's see. So, ooh, and it goes pretty fast. So let's slow it down. So first of all, notice here that, so at the very beginning, we're looking at the circle of radius 0.1, and it doesn't intersect the origin, or it doesn't wind around the origin at all. Look, so here, notice the x-axis is going from like minus 30 to minus 50. So it's far away from the origin. But okay, as we play this, so then, okay, so now look, the axis just came in. So now we have winding number 1, and then we can just keep playing. So okay, now winding number 2, 3, and 4. So this is a degree 5 polynomial that we started with. This is degree 5. And so ultimately, the claim of the proof is that for large circles, the winding number should be 5. And so, okay, so here, at this point, already very quickly, we've found winding number 1, 2, 3, 4. And so we could just play this and see what happens. It kind of looks crazy because I guess it doesn't like to render this. It can't render it very quickly. But okay, something seems to be going wrong. So here, do we already have, this is winding 1, 2, 3, 4. We're supposed to get winding number 5 if we go out far enough. But it just seems to be getting further and further from the origin. Look, it's just blowing up. It's going crazy. But are we sure this is 5 or 4? Maybe it's already 5. I mean, the things look close together. 1, 2, 3, 4. It looks like 4. All right, let's just watch it for a while. I can speed it up just a little bit. It just keeps getting larger and larger. Bigger and bigger. Is it still 4? I mean, nothing's happened. It's still 1, 2, 3, 4. Okay, let's see. Let's speed this up a little bit. So if we go out far enough, it's supposed to wind around 5 times. Let me speed it up just a little bit. Something is happening. There's a part that's getting a little closer to the origin. Oh, here it comes. Oh, this looks good. Okay, we want it to wind around the origin. Come on, you can do it. Around the origin. Go for it. There it is. There's the 5th one. So now 1, 2, 3, 4, 5. That's it. So cool.